Hi, everyone, and welcome to Big Data Today. Today we will have a guest lecture. I'm very happy that Ramon, who works at Google, will give a guest lecture about distributed system design. I know Ramon for nearly 15 years. We both worked at CERN in the past, and Ramon then got an offer at Google and rose through the ranks, and now is doing lots of big data work at Google and managing lots of people and building great systems. So I'm very happy to have you here today, Ramon, and I'll pass the floor to you.
Okay, thank you. Is my audio, my video, slides, everything all right?
All perfect.
Fantastic. So, as Patrick has said very kindly, I'm Ramon. I work at Google. I don't manage much people now anymore. Like I manage 0 people actually. So I'm a technical lead again, or an IC. So I'm in a group called Core Infrastructure. So we do infrastructure for all the company, search, GCP, you name it. Like in particular, we do things like privacy, safety, and security systems. That's my area of work, right? And I've been here for like a bunch of years now, like for a while. So and I think this is great to teach everyone what we do. So this year I have last year we had a session similar to this, and it was like very much focusing like the tools and stuff like that, right? Which this year I want to be focused more in like the principle, like going back to first principles, like how we do distributed systems and why we need distributed systems, right? So I don't have like content for hours, and I really don't want this to be a monologue. So any question that you have, you just go for it. We'll just stop and we'll just address the question, right? Because this is not we use science, but this is not like a closed science in this, or like an exact science for the design of a distributed system. There is always trade-offs, right? So you are going to have a problem that you need to, or a service that you need to offer, right, for doing something. Like for example, we were this morning looking into information retrieval systems, right, for building applications like RAG and all these things that we do with AI, right? So what is the trade-off of latency? What is the trade-off of complexity? What is the trade-off of cost, right? There is like a whole triangle of things that we need to balance, right? There's the cost, obviously, but there is as well the features and the functionalities that you have, and there is as well the complexity and the time that we need to bring this to the market. So it's not something that is trivial, or there is a solution that fits all, right? What I want you to offer you today is like a guide of like so when we have a distributed system, what are the angles that we need to take into account for making the trade-off, right? Like you are going to be engineers, and the career of an engineer is always making trade-offs, right? It's very rare that you find a solution that is like the only and perfect solution is X for a problem, right? So with that said, let's go for it. So distributed system design. So how you scale up system, right? Basically, I think everyone knows that you can run things in your own machine, right? But when you have some traffic, which is where you want to be, like, you run your company, you run your startup, you run your whatever, right? You want to have the problem of like, I have too much traffic for my service. That you want to be in that place, right? So what we are going to be covering today is basically 4 things, right? So, and then you let me know if there's something else that you want to know. The first one is architectural principles. Like, okay, so you go from a system that is running in one of your machines in your development or whatever, and then you have to distribute it for multiple reasons. There is a scale, but there is as well things like resiliency, right? So resiliency and reliability is very important for services to be successful, because if your service is great but it's not available, it's the same thing as you had nothing, right? So reliability is important. Distributed systems do help with reliability. So I want to show you how. Second is like going deep into like reliability. Even if you have a distributed system that is redundant and all these things, things happen. Your machines break, your data center catches fire, these kind of things, right? So how we handle that in the software, I mean, in the application, right? Then we have like some sort of, I want to touch about operations, right? Because the systems, they are alive. Believe it or not, once you write the code and put it in productions, that's always changing. Even though your application is not receiving new patches, because you are not releasing this week, everything underneath is changing. Routes of the internet are changing, like infrastructure is breaking, someone is deploying new machines in your cloud or whatever that is, right? So we need to see how the application is performing. And then I'm going to give you like an introduction of the SRE role, because I'm an SRE, so I'm going to sell you like my role, but that's the agenda we have for today. So with a photo view, architectural principles. For the questions, by the way, you can raise your hand or whatever this thing in Zoom has. If you're in the room, just stop one, and then I think Patrick can pass the question through the call. So let's just take one example that I brought. It was like, for example, this month, the Google Photos is making 10 years, right? So I make up the slides with this example in mind, right? It's like, so we have a photo uploading service, and like something like Google Photos, where you upload your photos, right? And there is some things in the background that they are happening. Like, for example, I don't know, you can search for your own photos, and then you can have things like AI functionality. So there is some background processing like in the server, right? Because if there's some enhancements, or you can get, I don't know, like reminders and these things. So there is a service that I think is well known. I don't need to explain how it works, but you have an app or a website. You can upload your photos, and then there is a retrieval for your library and these kind of things. So photos are something that is not trivial in the sense of they are chunky files that you can get from these phones and these like reflex camera that we have these days, that you can get photos of like 40, 50, 60 megabytes easy, right? So it's a system that is not trivial. If you have like billions of users or hundreds of millions of users like Google Photos has, you end up like having like a bunch of, exabytes of or petabytes of blobs hanging around, right? So it's not as easy as like I'm gonna just copy it like multiple places and that's it, because you might not even have like space for all that stuff. So we're gonna do one simplification dot for this example, that everything is public. In reality, nothing is public, but you don't want to upload your photos and have it in a public library for the internet, right? But I'm gonna just make it as such, not because like I recommend to do that, but for simplicity, for understanding how the system would work, because I want to focus into the upload and the replication and all these things. In reality, you are going to have an authentication, you are going to have user accounts, you are going to have all sorts of permissions, right, for only the users that they are like able to, yourself, or if you share the photos with other people, accessing those files, right? So the first thing that we do when we have a distributed system, believe it or not, is thinking about what is the requirement. So what is the problem that we need to solve, right? Because there is like a huge difference depending on the outcome of this exercise, right? So if you have a service, for example, I run at home photos storage as well for my family, because we have like, for my parents and so on, for running like and seeing some pictures and so on. The number of users that this service has is 4, right? So I can basically deploy a Raspberry Pi with a couple of disks connected via USB, and I'm done, right? Like there is no more thinking that I need to do. Probably a backup, but that's about the whole story, right? So it doesn't cost a lot of time. I can get software that is out of the shelf, just deploy it there. People can see the pictures. I'm done, right? Now, if you go and say like, I'm have a startup and I want to have like I don't know, for example, a couple 100 million users because I need to be successful. The restrictions that you have, the constraints are completely and absolutely different, right? Because then there is like, for example, where your users are located, right? So in my place, I'm in Switzerland, my family is in Spain, so it's like, just dump something in Europe, mostly it's gonna go, right? If you have users in Australia, you have users in Africa, South America, North America, Asia, right? The constraints that you have, they are much stringent, because you cannot just drop things in Europe, because the people that is in the United States, for example, they're going to have a transatlantic network pipe that they need to connect through. That's like 140, 135 milliseconds round trip time, right? So that's, if you are making a few calls, that's very noticeable, right? If you're loading a gallery of pictures, you need to load all of them, right? So if you're going to do like, show 100 pictures, like thumbnails and this stuff, and you need to go through the Atlantic like 100 times, right? You're going to be around like, 10 seconds loading your page, right? Give it or take, because of all the assets and all the things that you need to have, right? In second one, the user will just leave. So your application will not be successful, even though might be just beautiful and very nice, right? So that's a constraint. Now you need to be present in 2 continental locations. So you are now reasoning about a distributed system, because you are going to have like, different instances and different things, right? There are more constraints that you need to think about, like, for example, the data volume. So how large are the pictures to upload, how many pictures per users, and so on, right? There might be the case that you cannot load this into a single machine or a disk, that I was saying for my photo libraries. You're going to need to have like a cluster file system and so on. You're going to have replicas of the pictures, because what happens in one of the disks like goes kaput, right? And these things. The traffic, right? I think the traffic is something that's very important, right? The QPS we use at Google, we speak about QPS because it comes from search, the queries per second. You could see these as requests per second in many places as well, equivalent, right? So if you have, you have 100 million users, but then you have one request a day per user, right? Okay, that's handleable, right? If you have like something like search, that you have like, for example, search or any other system like Gmail and these things, that you have many users, but as well, each user is going to use your system 10 to 100 times a day. Search, you can use 100 search per day, right? That changes the story, because even if you have 100 million users, you're going to have like a billion kind of queries every day for your user volume. There is as well the shape of the queries, right? So the traffic is not smooth. So you are going to have traffic that goes like, people wake up 6 a.m., 7 a.m., 8 a.m., you have the peak, right? Then there is the daily traffic usage, and then there is the trough on the night, right? This will happen in Europe, this will happen in the US, but they will be shifted in time as well, right? So you need to calculate the traffic that you have is not smooth around the day. You're going to need to say, like, what is the peak that I have? And you need to provision for that, right? And you need as well to see, like, well, if in the night I have less traffic, can I do something with that compute capacity that I'm going to have? So all these things, they need to go into your requirements, understanding of what is the system that you are solving for, right? You have three resources that you're going to be able to use. I think you might understand this very easily, because you have time. Time is a resource that is constrained. You cannot say like, hey, so we want to launch a competitor for Google Photos, right? And you're the startup and we're going to need, 10 years to build it, right? You're not going to be able to get to market, right? So time is something that you need to minimize. You need people, right? But as well, it's not that you say like, hey, instead of 10 years with 10 people, I'm going to do one thing. I'm going to put, 1,000 people, right? And I'm going to divide my time by 100. So I can do it in like, the 3 months kind of story, right? That's not, because there is cost of communication, there is cost of coordination, right? So you cannot have as well infinite people scaling infinitely. So it's something to consider. And then money, of course, because you need to pay people to start with, but there is as well machines that you need to use, resources. There is an opportunity cost. You might have investors and all these things. So money is something to consider, right? So with these three resources, right, you have the classic triangle for the project, and you need to say, well, and then there is the technical constraints, right? And you say like, well, my feature needs to go here. So you are going to need to prioritize like, oh, we are going to take longer, or we are going to drop more people, or we are going to just, drop more money, because what we're going to be doing is, for example, a system that is less efficient, right? Duplicate more kind of thing, have system that is less well coded, stuff like that, right? That's money, right? But might make you get to the market on time, for example. So these all things are to consider, right? You might want to run on premises, or you might want to go to the cloud, right? All these things that the requirements, you can knock yourself out. You can find requirements as much as you get. But let's say you settle into one way of doing it. You know what is the size of your market. You know what is more or less what the user is going to do with your service, how many, in this case, pictures they're going to upload, and all these things, right? And you say like, we're going to build it in like 3 months, or like 6 months. We need 10 people of different roles, right? And we're going to need like €1 million, right? So you go, you say like, we know what we're going to be doing now. That's easy, right? Because you learn the code and you're good, right? So you start with saying like, we're going to do first a prototype, right? This is my Raspberry Pi at home. So I have a machine. It has the application logic. In this case, it's software that is off the shelf, right? This image, if you want to try it out. And then there is some storage. I have a USB disk, and there is my pictures there. This covers my use case for now. Now I want to scale it up, right? And I want to say like, hey, so what about getting more users, right? Like we need to scale it up. Like at some point, the single machine is not gonna like be sufficient, right? You're gonna be surprised how far they are going to take you, right? So don't optimize prematurely, right? Sometimes just a machine with your stuff and a backup, that's fine, right? And when you scale up, you just say like, give me a bigger machine, right? And that's usually like, it gets you far, right? And it's fair. saying like, hey, to scale up, what I'm going to do is like deploy a bigger server, right? That's okay. There's going to be a moment in which you cannot, because there is no bigger server, right? Or you need things that a single machine cannot serve. Like, for example, you want to have customers in another continent, right? You cannot just place your server in the Azores and just try to like have like half of latency for everyone, because that's probably not realistic and not even like covering your use case, right? So the first thing that you do to scaling is like, okay, let's say that there is no bigger server, right? We're going to remove the state, right, to a specialized service, right? This has another benefit. It's not only that you are saying, I'm going to have like more distribution, so I can have like 2 machines. There's more load that I can handle, but there is as well one different thing is that you are creating something that is stateless. So state in the applications and in server is a liability, right? Because you need to, when you store things, right, it's not only that you are going to have a database and you are going to need to have something that is persistent, right, which implies backups, which implies like, there is going to be data redundancy, there is going to be like a data integrity that you need to have. There is going to be like, for example, when your application, you change it and you might change the schema or something, you might corrupt the data. So you need to, so it's a liability by itself, right? You are going to have it because you are going to have it, right? But the better logical separation that you do, right, you can have people in your team that say like, I'm going to focus on storage, right? For example, we have in our team people that is specialized in storage and so on. They know what to do, right? And then we are going to have people doing applications, and they can go much faster because, they know that the storage, it has a clean API, whatever that is, a relational database, for example, Postgres, MySQL, all this stuff, right? Offers a simple API that is you create SQL queries and there's a schema, right? Usually leaks the schema, so that's an abstraction you might want to abstract with something else, right? But in principle, once you have separation in the APIs from all the application logic and the storage, right, the people that is doing the application, they don't need to care about data integrity or data reliability, whatever. They know that they can send an RPC or a REST call or an SQL query to an endpoint, right? And they're going to be able to store and retrieve the data. That's it. Storage, though, has another problem, that is it's a liability as well, in the sense of like the recovery, the properties of like the coordination, right? It's very hard to separate. So when you have different storage systems, right, the partitioning a database is not easy, right? Because you say like, hey, I want to have a database that is partitioned, half of the data here, half of the data there, right? Okay, now how do you, for example, ensure relational stability or relational, I think, like foreign keys and this kind of stuff, right? Cross machines, very difficult to do, right? So how you are going to partition all that, we're going to see later, right? But it's difficult. The application logic, for example, once you remove the state, right, it's just smooth, because it's just, if you code the application well, right, and there is one thing that is called the 12 principles for applications to do this. In theory, you can scale it ad infinitum. You just start adding copies of the same thing. You can have something like Kubernetes, for example. It's like, look, I have this container, is running my application, scale it up via a metric. You tell like, when the usage of the CPU for this application goes over 80%, deploy another copy automatically. There's going to be a load balancer and stuff like that. So that's in principle for free forever, in principle, because things are not for free forever very long. Storage is another story. So how we scale these things? You can scale two ways, right? Vertical scaling is what I was saying, like, hey, so make things bigger, right? So if you have one machine, make the machine bigger, like get more cores, get more RAM, like whatever it is. If you are in a cloud, this is automatically. If you're running in containers, you can say like, give it more CPU to the container, right? Vertical scaling has limitations as well on the contention and things like that. If you run, for example, this is a case that we were debugging this week, a Java application, right? It keeps scaling because, more CPU, why not, right? It gets to a point where, for example, you are going to have contention with the threads that the server is running. You are going to have contention with other applications that are in the machine. You are going to have things like the memory bandwidth, like, you can give it a lot of memory, that the memory bandwidth is a limit of all the operations that it can do, and so on, right? So at some point, you need to combine this with horizontal scaling, which is make more copies. What I was saying, like deploy more copies of it, right? Usually you can do both as well, right? So say like make more copies, but as well like adjust the size of each of them depending on what it's doing, right? When you do this two-dimensional scaling, things are starting to be complicated, and there is a whole lot of like multivariate optimization that you can have, because like, okay, when do I decide to go up or horizontal. So do I prefer prioritize more copies or bigger copies, and so on? So there is some limits that you need to put into the system, right? And in generally, the bigger you want to have bigger and fatty replicas, because that's more efficient for certain resources like CPU and so on, but not too big. So it's not easy. Like you need to find, depending on the application, right? You're going to need to find like how you do these copies, right? How you do this replication, right? There is as well another problem with the horizontal replication. It's like, well, you now have 3 copies of your application, right? So when there is a request, where it goes, right? So where do you send it, right? Do you send it to replica 1, 2, or 3? Depending on the usage, you might overload the first one or the second one. Is this something that if it's a request that comes from the same user, are you going to always do the same replica, right? So there is some caches and some things that might be helping you with performance, right? If you want to do that, where do you have the state of like what the user goes where, right? So you see that this is a rat hole that you can just go and go and go in complexity forever and infinitum. But this is a principle that you need to know and that you will use, right? You will do vertical scaling and you will do horizontal scaling if you have an application that has a bunch of users, right? So let's just say that now we say, okay, so we have horizontal scaling, we're going to have multiple replicas and so on. There comes the load balancer. That's answering the question of like, okay, so for the incoming traffic, now that we have more than one replica, potentially more than one machine, right? Or ideally, where is the traffic going? So you have a load balancer. A load balancer is not a trivial thing to implement, right? Because if you start seeing this stack that we have, they are what we call single point of failures. So you have the load balancer. If the load balancer fails, right, you are out. It doesn't matter how much replication you have in the rest of the stack, right? If the load balancer is out, you are out, right? So this is a SPOF or a single point of failure. Same with storage in this stack. Your storage is out, it's like you might have the most beautiful and perfect microservices with a Kubernetes cluster, multi-deployment, with automatic scaling and so on. You cannot serve because there's no storage. So the system, you need to look at it holistically, like when you are deploying or designing a distributed system, because there is this theory about the bottlenecks, right? When you optimize something, a system will always have a bottleneck, right? Or a single point of failure. So when you optimize one part of it, right, a new one will emerge, right? In this case, we solve the application layer, but we have now 2 single point of failures, this load balancer and the storage layer, right? So we say like the further step that is like, I'm gonna want to have different machines, right? So for example, in the photo album application that we are talking about, right? You might have the applications, the yellow thing, right? That is the application server. It's like serving pictures for everyone, right? So you have the load balancer and it's just beautiful. It goes through the continent, to the US, it goes to Europe, has some caches, auto scaling and so on, serves pictures really well. That's a simple server because it's like, it's a blob, you just need to find it and serve it. But now you want to add a feature in your application that is, we want to do facial recognition kind of thing, this thing that you can search by like similar pictures. So you see my face and then you see photos that they has my person in there, right? And it's a machine learning model, right? Like a clip kind of thing, right? Like a classic, right? Or semantic search on images. That is what clip does, right? You can say like, find me bottles of wine in my library, and it's gonna find you like by this search. But you need to run a machine learning model now, right? And might need to do things like a batch processing. So the portable application server is different because you might need a GPU, for example, for these machines, because it's running a model you want to accelerate, or a TPU or whatever, right? Or it might be a machine that has a different shape because you need to have much more memory to hold on the memory for the model, or something else. So you want to specialize that for being cost efficient as well, because you might not need, for the simple application server, you don't need a GPU. So they are expensive, so you just deploy the GPUs in your server. And might as well have another trigger. So it might be that these machines, they are not be serving like demand that is coming for the users directly, but is using some batch processing. So like when someone uploads a picture, right, you just put it in a queue for it to be passed through the machine learning model or to whatever it's doing, right, and then store the results in a database, so then you can search it, right? So this gives you as well flexibility for saying, hey, so I don't have all the compute in the world, right? So let me do one thing, that is when we are at peak traffic, right, we'll just prioritize serving requests to the users, right? And when we're at trough, right, in the night, then we have less compute. These machines will get more compute, so they can process all the libraries of users in the night, right? Store the results in the storage for them for searching, right? And the day after, users can start searching with like fresh data, new models, whatever that is, right? So you need this separation of servers, right? Basically, to be able to deploy them and so on. Deployments is another story. You are gonna want to deploy new features in here, right? So you might have the opportunity to select, with this setup, I can do 5 deployments a day for the application server, because there are some machines that I control and I can deploy and restart or do whatever I want, right? Without affecting the other part of the application that might have another velocity. You might need less deployment, right? You might need another kind of story, or you might need to deploy ML models. We have another, they are going to have another validation that the thing that you do for a Java server, right? So this will give you more flexibility, and probably it's going to be most cost efficient as well. So now you say, it's great. We won at this. Like, we have like an application that it will have like hundreds of users all around the world and so on. So we just put this thing into different data centers. That's what you want to be, like the complexity of like, we have a successful product, right? So you have different data centers, X, Y, and Z, right? And then you have like a whole stack in all of them. You are going to have storage in all of them, and you're going to have your load balancer and stuff like that. There are questions in this architecture that I think they are fair to ask, right? Does anyone have a question about this architecture before I do the questions myself? Okay, cool. So first is like, you have load balancer per cluster or per data center. Fantastic. This is single point of failure, right? But you can mitigate in another way. If the load balancer, for example, in data center X is out and this data center goes out, you can redirect traffic to another data center. Okay, good. That's something we do in many services at Google anyway. And many is like a common practice, right? Fine. So you want to have like a simpler data load balancer setup, and you can have resilience in that way. Fine. You need to start counting of like, well, if you're going to have this kind of like redundancy, right, or resiliency, there are 2 questions in there. First, if I would need to move all the demand that I have in data center X to data center Y, there are 2 questions. Like, will I have enough compute capacity for serving that? Because that data center will need to serve the natural demand that it has, plus the demand from another data center that is kaput in that moment and will need to be absorbed, right? So you're going to need to over-provision these data centers to have capacity for absorbing the ones that they're missing. For example, in this case, when you have 3, right, you may have a setup of n+1. n+1 means that you are going to have the demand for n, that is your entire data set, plus 1 of redundancy, right? So these 3 data centers, there is one that is going to be always running more or less empty, right? Because that's the redundancy, right, of the system that you have, right? So your maximum utilization gets down the more +1, +2, +3 that you are adding, plus k in general, right? If you have a very, very reliable service, right? For example, in my job, we have a service that validates the cookies. So you have whenever you present yourself against Google into a product or into an API or whatever, you're going to have an authenticator. Could be a cookie in the browser, could be a no-auth token, could be like some API key, whatever. We need to verify that, right? So the system is like a semi-single point of failure in some sense, because if we cannot verify the authenticator, we cannot know who is the user that is calling us. Is the user authorized to access this API? How we can redirect it to your inbox and not other people's inbox, this kind of stuff, right? So this system, being something that is as central as the load balancer in this, it has a very high reliability target. So it will have like about 6 nines, right? Meaning that the downtime that you can have for this system is going to be no more than 1.5 seconds per year. So 0, right? In practical terms, 1 second is just something that you need to design the system for not having ever a downtime, right? Another option could be, for example, some systems that you could have maintenance downtime. In how many times in your bank you have seen in your app in the bank saying like, the bank is not available this Sunday because we are doing maintenance, right? If you can afford that, that's fantastic, because you don't need the complexity of like not being able, or design a system for not being able to fail, right? But let's say that you cannot have that because you want to have your application available forever, right? So in this case, you're going to need to have this redundancy. So to achieve very high level of redundancy, you might need to go not only to a +1 and have 3 data centers, right? You're going to need to go +3, 4, 5, right? So you can tolerate the loss of 4 data centers and still being able to serve the totality of the demand, right? So that's more complexity. The other thing that this picture has that is very important to consider is these very gray arrows that they go from data center to data center, linking the storage, right? Storage is a liability, I'd said, right? Because now you need to have redundancy in the storage. So you need to have, if data center X goes kaput, you need to move people to data center Y. So we assume that there is capacity there. You over provision, so the system just scales up naturally and gets the traffic, so it doesn't die. Now, is the data for these new users that you were not intending to serve in this data center available there? Right, because if data center X is gone, right, you are going to need to serve from the other location. But at the end of the day, the requests they are going to go through to the storage. Is the data there, right? So you are going to need to be recalibrating and replicating all the storage data centers, right? So they all have all the data in this design, right? So whenever a user goes to data center X, that is in Germany, for example, in Frankfurt, a typical place for data centers, I upload my pictures there, right? Frankfurt goes out because there is a power outage, right? And then we're going to go to data center Y that is in Paris, right? That's completely transparent to users. Latency is going to be invisible, the latency change, right? For a user that is, I don't know, in Bavaria or in Switzerland, right? And I go there, get my traffic, my data is not there, therefore I get a 500. It's like, sorry, we cannot serve you, right? That's equivalent to the user to an outage that happened in Frankfurt, right? So the replication on the storage is hard because then if I upload my pictures in data center X that is in Frankfurt, right, then I'm going to want this system to copy over the blobs of the pictures to the other data centers. So in case this one goes out, I can immediately be served to the other, right? There is all sorts of data management and data integrity problems that you can imagine here. If this is a blob service, like the picture uploading service, it's not too hard because you can just start copying the files to the other places. There might be a window of time where you are vulnerable in a sense of like, you upload the picture and then in the next 2-3 seconds it's going to be copied over the other data centers. If data center X fails at that moment, there might be some pictures that they were not copied, right? Just at that moment. So you might want to handle that in different ways. You might want to say like the picture is not uploaded, so the user doesn't have the expectations of the picture is going to be available. You might say like, this is eventually redundant, so there is some pictures that they are not available right now. You are going to see them in a minute, right? When the data center X comes up. Your choice. This is a product choice. If this is a storage in the form of a relational database, for example, things are harder because you might want to emit a write to one of the databases, one of the data centers, like X, for example. That write happened, right? And then you need to replicate it to another database, like the row that you put in there, right? And it needs to be consistent, right? Because it's not adding. Usually, you might want to change your password, right? So you might have the password, old password in data center X, old password in data center Y, right? I change my password. I go to Frankfurt because my place, right? Okay, so now data center X has the new version of the password, right? This thing will replicate to the others, right? And then you can just log in from wherever you want. But if it fails at that moment, right, you're going to have a system in an inconsistent state, right? You're going to have like if data center X goes out, password has not been replicated. When I log in, right, it's going to reject my new password, right? And that's a problem because it's like, what happened? Did the password change? Did not? Then when data center X comes up, then the new password comes in and it's all a mess. So you need to handle this. There are many ways to do this, right? From the complexity of like saying, hey, simple complexity, like built-in replication that some databases have, that is like, you're going to have multiple replicas. And when you emit like MySQL, I think supports this, for example, you just emit a write, the replication will happen, and then the database where you are writing will return, say, like the write was settled in multiple replicas. So you know that if we return to the user, this functionality is consistent across the board, right? You might want to have eventually consistent database. Cassandra, for example, is eventually consistent database, right? Which is like, sure, I'll write here to the database and then you just replicate, right? This still needs things like, for example, one thing that I recommend you to read is about leader election or consensus algorithms, right? Paxos, Raft are examples of it, right? It's like, okay, so now let's say you have all these three databases, right? I want to emit a write. I want to modify something in my user profile, right? Okay, which is the database I should go to? what is the leader at that moment, right? How you choose that in a way that is idempotent, right? So there is no a single point of failure in a way, right? That the three databases, they can coordinate, right? And they say like, okay, I'm the leader now, I'm going to receive the writes, and then I'm going to send the mutates to the other replicas that I have until things are consistent, right? And when one of the databases fail, there is a new leader election, right? So you don't end up with saying like, okay, data center Y failed, right? And now you can emit writes to X and C, right? And then two writes happen, right? Which is the one that needs to win at the end of the day? This is what a consensus algorithm will solve, right? So data is hard, right? So what did we do here? Basically iteration, right? You are not going to get to a design in the first round, right? And the requirements and the necessities or the needs that you have in your system, they're going to evolve over time, right? It's not going to be settled in stone, right? Even systems that they are like what we call legacy, or they are older, or they are something that is like more mature kind of architecture, like, I don't know, a banking system, which is, we understand very well what a bank should be doing, right? They're iterating as well, because there's a new regulation coming in, and now you need to do instant payments, right? That changes the whole thing, right? So your system will need to take it in there. So there is like a component as well of maintainability that you need to have, right? So every system will have bottlenecks all the time, right? And when you optimize the system to remove one bottleneck, another one will appear, right? So you are going to need to make sure that each of the functions that you have will be able to scale. In the example that we have here, let me go back, right? So you have things that they are very much scalable, like the application servers in the middle layer, right? That's very, very scalable, right? Load balancers is something that, well, this per data center, so probably is fine, right? They're going to have a limit of load that they can handle, right? But maybe it's just sufficient for what you have. And then there is storage, right? Which is like, you have disks, you have writes in there. So probably in this system, the bottleneck is going to be the storage, right? But who knows? Then we talk about the single point of failure and weaknesses, right? I think that's something we need to be and understand it. You need to embrace the fact that you are not going to be able to do an invincible service, right? So you are going to have to take some risks in the sense of like, you are aware that there is some parts of the system that they are less redundant or less reliable than others, right? But they are enough. I think that's something you need to get. If there is something you need to get out of this class today, is the enough, right? We can all go through the rabbit hole to say like, I'm going to create the fabulous, like, invincible service, could scale to 7 billion users, right? But if you have 100,000 users, right, it's cost that you don't need. So what you need to build is a system that is enough good for the requirements you have, so you can build this as fast and as cheaply as possible, right? And then as you grow, right, make sure that the system evolves with you, right? That's important, because you need to do something that is efficient, that is economically viable in a sense, right? And then the how you accommodate the change. If you try to build an invincible service, right, you might have a service that is unmaintainable because it's so complex that no one can understand it, right? And that's something that we need to be aware of, right? Okay, so about principles and so on. I'm mostly done here unless you have some questions, and we can go to the other section. So no hands, no questions. Perfect. You can make them at the end. Oh, there's a question. Boom. So it's in the chat. I'm gonna read it for people that is not seeing the chat. That Elmer Dema said like, what about the tech stack? What language, database, etc. What do you use in the example you explained? Would appreciate if you could also explain the reason for each. Okay, we can do that. So let me go back to the thing, to the diagram, right? So first of all, depending on the system, we have a lot of Google. We have a lot of internal infrastructure that is custom made, right? But we are using more and more and more open source and public and cloud stuff, right? So a system like Gmail that was built 20 years ago, right? We didn't have cloud and all these things, right? And in many ways, we are still like one of the biggest networks. So some part there are no services that might fit your purpose. So don't be afraid to build your own. If you don't find anything that doesn't fit your purpose, that's something that you have in your sleeve as well. Generally, I recommend to avoid if possible because it's costly, right? So you have to have a good reason for it. But in a stack like this, for example, this is a service that deployment is very common across, I think, the industry, right? And in Google, we certainly have this stuff, right? So for load balancer, I'm going to go from top to bottom. Load balancer, that's something that is more or less solved in GCP. So you have something like the Google Cloud Load Balancer, right? it has two levels. So one thing that is not in this diagram is like, okay, you have users, there is the ISPs, right? And then there's the Google data centers, right? Or your company data centers, right? How you get from these to your company data centers, there's going to be load balancers, like, for example, the DNS. You need to publish that. You need to publish the DNS in such a way, like when someone types photos.google.com, they are to a closed data center automatically. So there is no like a global kind of singular thing that they need to visit. So they can start going to data centers automatically. DNS is very flexible and is very great for it. So use it. Then for load balancer, there is the GCLB, so the Google Cloud Load Balancer. If you are on premises and you use Kubernetes, they have like a lot of it's called egress nodes, right? So there is multiple versions of them, right? The one I have used particularly successfully is the Nginx. It's like a great kind of like application proxy in this case. So it's going to take some load and so on. So it will act as a load balancer in a way. For the middle layer, right? I think that's more or less the one that we have more clarity. There is services like Kubernetes if you want to run your own containers and your own applications so they scale. But there is as well cloud providers like, so in Amazon, in GCP, you have things like Cloud Run. So you say, hey, my application is this container, a Docker container, run it, right? And it's going to like scale it, deploy it, put it behind a load balancer and so on. So it will remove quite a lot of your operational load, right? I think running in containers is something that is like more or less do containers. Basically, there's no other way these days. So it's flexible. Package it in a Docker container. You have a Docker file. It gets built. You have binary. You can run it more or less wherever you want, right? So it's like super flexible, right? Technology for the servers. I would recommend you to go through language that is mature, right, and is memory safe as well, right? Writing in plain vanilla C, there might be use cases, so there might be a legit use case because super performance or whatever and so on, but use something that is like memory safe because it's going to remove you the burden of a lot of vulnerabilities and stuff like that for security. So Java, Go is very nice. For example, if you need to do multiple concurrency and so on. Rust is something that is really getting popularity because it's memory safe, but it's really performant at the level of C++, right? So a combination that we use very common on Google is to use Java for front ends and stuff like that, where there's a lot of data validation and so on. So it's very convenient. And then for backends that need performance, we typically use Go or C++. Like more Go these days, but C++, we have a very large code base in C++. If you need to do things like crypto, if you need to do things like machine learning and so on, you want to be in close to metal performance, right? So you don't want to have a VM in the middle, right? For these particular cases. This is why this setup of like having the yellow server in Java and the purple server in C++, for example, is very common and very useful and very nice to balance, like, speed and performance. And then for the storage, that's the crown jewel question. Is like, how do you put storage or where do you put it, right? One application that we use or one system that we use across the board is Spanner. So Spanner is a database that will handle replication. It will handle like transfer of mutates to different regions. It's gonna handle for you the things like the choosing what is the leader of the transaction at that moment, and it will offer you an endpoint that is SQL, right? So SQL is like super common. There are many ORMs, there are many system frameworks and stuff like that will create SQL for you. So having an SQL endpoint is really convenient, right? So you can just define your schema as a relational, more or less, as a relational database, right? And then query it like that. You have joins, everything, right? So it's really, really great. At some point, you might need something else, right? That is like, I need a cache. I need something that is like a key value store, for example, is very common as well. There are other options that you have things like in the open source world, you are going to have things like Cassandra, for example, for key value store, eventually consistent, very great. It does replication for you and so on. So for certain data, you might want to store it there and so on. And then underneath this, there's something that is not in this diagram, that is the file system, right? So the file system, you want to have like a distributed file system to forget about like doing the backups and replications and so on, right? Things like Ceph, for example, CEPH is very useful. So you just say like, hey, or ZFS, if you are into that, it's like you say like, hey, I have a bunch of machines, right? create me like a virtual volume for all the disks that I have in all these machines and so on, and then you build on top of that. So when a machine is removed, right, the thing will just resilver and then will just rebalance, and then you add a new machine, it will start rebalance and adding the new data and so on. So you don't need to redo your database on top of it, right? So the gist here is to, from the metal to the load balancer, start adding abstractions, right, that it will make your application and your life easier, right? At the end of the day, the reliability is going to be built in the application. So the application will need to be aware to have failovers and so on, because it's the only place that you can have the full, reliability implementations. But in each of the layers, you can add more functionality. You're going to start virtualizing in a way, right? So you can have like a large cluster file system in each of the data centers where you can lay out the database on top, right? So the database doesn't have to be aware of like what disks are available and so on, and then you can swap them in and out, right? In the same way, the application, once you have a database, you don't need to, the application knows that it's going to send queries to a place and data will come, right? So that's it. And then the load balancer will help you, like, put the load where it belongs, kind of thing. Okay, I hope that's answered your question. If not, do let me know if there are more concerns there. So now, how we do fault handling? This is very important because we need to tolerate errors, right? So this is one of the most difficult parts, right? Because the system, you can get a distributed system that is very nice, right? But never works, right? Because everything is failing all the time. I know in my infrastructure, some amount of machines, they are broken right now. Some amount of machines, they are restarting because of a kernel upgrade. Some amount of machines, they are in a data center that has a fire ongoing, or a data center that has fiber cuts and all these things, right? So I know that all this is a mess. Production is very ugly in a sense, right? Because everything is broken all the time. But we need to build applications that they are mostly always available on top of these non-trusted and non-available components. So how we do that, right? As we were saying in the previous slide, there are many ways to do it. In each of the layers, you can add some reliability, some functionality, some abstractions, right? But at the end of the day as well, the application needs to be able to handle the faults on any other underlying system that you have, right? In the same way that you have a distributed system and you put on top of the database, right? You're going to have an easier time, but the database, you are going to make backups of that database in case the failure that you have in your distributed system for your distributed file system is catastrophic, right? You are going to have backups there, right? And you are going to have redundancy on top. So you're going to go all the way to have redundancy in all the layers, right? So component failure is what I mean machines or disks are broken. This is the most common. We build these days, I think everyone is building with commodity hardware, so you don't build with like Cray supercomputers and these things. You just go to, I don't know, whatever brand, Dell or Microtik or whatever it is, and say, like, give me some servers, and they are going to have a Xeon processor, RAM out of the shelf, and some disks, right? That's how you build, right? So the thing is that there are many components, because it's not only the machine. There is a rack where the machine is put. There is the power supply unit. There is the top of the rack router. There is the distribution routers. There is the fiber links to your data center. All this stuff. Anything in that is subject to failure. So how we do that, right? First is considering single point of failure. Is anything in your infrastructure that if it fails, it will take down everything with it, right? So that needs to be understood. The system design based on the principles that we have before is very important for tolerating these kind of failures. Another way to do it, right, is a query of death. Query of death is a nice, catchy name for a bug in the code, right? So software is something that can fail too, right? And it fails all the time. So you write your server, right? And then depending how you prompt it or depending how you call it, right, it's going to crash. A typical case is like, you send a query that has some change and so on, right? And then there is an out-of-bound access, right? And it crashes the server, right? This is what is called a query of death, because every time you make a query with these characteristics, it's going to kill your server, right? So no matter how many replicas you have, right, the user with a query like this is going to go kill one server, and then he's going to retry. The server that was dead, going to go to another replica, is going to kill it, and so on. So if they keep retrying, they're going to keep just destroying your server one after the other, right? So this is purely a software problem. So the optimal solution is to write software with like principles and high quality, unit test, all these things like good validation and so on. So you reduce the probability of a query theft happening. But as well, you need to have mitigations in production, right? And you're gonna need to say, like, for example, hey, so for this kind of traffic, we might as well block the user for a while to protect the rest. So you might want to say, like, hey, this user is sending query of that. It's not intentional, so it's not like a hacking attempt, or it's not like a spam, right? But we are gonna block it anyway because it's gonna otherwise kill the rest of the service for the rest of the users, right? We'll fix it, and then we can just readmit this user that has this particularity, right? So what you're going to be doing is, like, say, like, when your page, right, and you have an alert, hey, your system is dying, you say, like, oh, it's a query of that. Then what you do, what I do is, like, I put this user on hold, in a sense, right? Fix the server, do a rollout of a new version that has, like, the query of that problem solved, and then you can readmit the user, right? It's not great for this user, right? But it's always better than just tanking the whole system that you have for the rest of the users, right? So the experience is not great, but it's the best you could do. Overload. This one is the one you want to have. Overload is like you have too much success, right? Basically, there's too much traffic, right? So that's good. You design the system for handling, like, increases in load. That's fantastic. But overload can have a problem, that is, it can take down the whole system in what is called a cascading failure, right? So you have, in the diagram we were showing, like, one of the application server is overloaded, right? Then it crashes, and then sends the load to another one. It crashes because they are, like, the cluster of Kubernetes is killing them, right? So you just take down the whole system in there, right? So there are many mitigations to do it. The one that is great is the load shedding. Load shedding means that there's some load that you're going to drop to the floor. You're not going to serve to protect the rest, right? And how you do that is priorities. We were talking before about, like, having different types of servers. One that is serving the users interactive traffic, and another one that is processing in batch pictures for, like, creating, like, a metadata out of the picture for searching and these things, right? In this dichotomy, when you have the system at load, because there is, like, everything is overloaded because you launch a feature that is popular, right? You know what to shed. The batch traffic is gone, right? So you will create capacity for serving the interactive traffic, which is much more important because it's what the users are perceiving at that moment, right? And then you just process the batch traffic in another moment, right? You just wait for the night, right? And then you just start up this traffic again to protect the interactive traffic. So interactive versus batch is a clear priority for shedding some load and protect the system, right? Another thing that you can do is drop overload. It's like, okay, my system allows for 1 million queries per second, right? I launch this feature that is super popular, and I'm receiving 1.3 million QPS. Drop 300,000 to make sure that the system is running at capacity. Because as well, think that with load, the latency that you are serving is non-linear. So the system is going to be fine until it reaches the capacity point, and then the latency is going to just balloon because they are shared resources like disks and so on, that they are going to be super contended, and then your service quality is going to, like, deteriorate for everyone, right? So it's better to say, like, I'm going to just serve less, serve it well, and then some other people will need to wait, right? Or you might need to share that load and just not serve it, right? And of course, the auto-scaling will help, but the auto-scaling will have some limits, right? You might just not have more machines anymore in your data center, right? Until they come, so you are going to need to have other measures. This one is as well a fault, and I think it's the last that I want, yes, that they have is the global change vector. This is something that we suffered many times in many services in the company, right? Like a few years ago when I joined the company, for example, the authentication service was a global thing because it's what we needed. It was just enough, like what I saw at what I said at the beginning. It was just enough for the use case. Then we had the GCP coming in, right, and say, like, hey, we want to offer these features and so on, and customers, they're going to have some guarantees of isolation and so on, right? So in this case, you can have a global change vector because if I break this system, I roll out a service, right, and it's subject to a query of that, right? I might take down the whole system for everyone, right? So I'm not fulfilling the business needs of, like, services that are going to be compartmentalized depending on the geographical region where they are, right? So you need to rewrite your system and modernize it, right? And it's the job, basically, right? There are many global change vectors that they go unnoticed. Many times we say, like, hey, is your binary where you build in your Docker image and then you roll it out with some CI/CD or whatever, right? That's the global, is the asset, right? So we look at a lot of at that. So we have pipelines, we have, like, continuous integration, we have, like, tests, unit tests, integration tests, right? But then someone comes in and have a config file that is hanging in a file system, right? And all the tasks, all the replicas, everything that you roll out, like, greatly, they're all reading that file. You push that file, it has a syntax error or whatever, and everything crashes in one go. This happened. I had one of those. I did one of those in my Google infrastructure, right? So watch out for these things, right? Because they can, like, you can put a lot of effort in many other things to say like all these replicas, everything, and so on, right? And boom, and you tank it in one go. Schemas of databases are another global change vector, and usually goes unnoticed in saying like, hey, I'm gonna change this table to have this other field, right? And then you change it, and then all the tasks, everything that was like perfectly rolled out, right? They cannot make the query that they are making because there's a column name change or whatever, right? Or like some foreign key that it was not well set up or whatever that is, and they are all failing at once, right? So no matter how much replication you have, this global change vector will take everything with it. So very important to watch out, and very hard because you're going to need to be auditing and looking for them and so on. Okay, last stuff. Questions, comments, concerns? Good? Good. So how you manage a system like that? You go to the place that you have all the system deployed, you have more or less a control of like, fault tolerance and so on. You have a system that is fulfilling your things. How you observe it? So first thing is monitoring, release management or change management, and the uniformity, right? So the uniformity is something that is just useful in the sense of like when you have many components, if you can't have components that they are homogeneous across the board, right? Is making your life easier for saying like, hey, all my application servers, they are Docker containers, right? So since you know that they are all Docker containers, right, you have some abstractions that you can assume, right? You can know that they are run by Docker. You can introspect them with certain tools and so on, right? So that's good. Sometimes you cannot, right? So the more uniform, the better. Don't overdo it though. Don't stop your development just because the thing needs to be uniform, because sometimes like it's better to have something that works on a service that is serving than having the perfection, right? Monitoring is important. Monitoring goes into two phases or two like types of things. Monitoring in terms of like collecting time series and seeing how the performance is. Like, for example, you see what is your utilization of your servers and all these things, right? So that's great. But as well, you need something else that is called observability. And there is a slight difference that is you might need to see how the system is performing introspective. Like, for example, traces, logs of things that they are happening, events of like, a user called the front end, and there was these other calls to other services. It was the return, there was the latency, these were the things. So you can have like the call tree in there that they did. So when you debug it, you have like a very rich trace of like, okay, this is not working, let's see why, right? And then you see like, okay, we are serving errors to these kind of users because this server doesn't handle well this, or there is like a long latency in this query, right? And then you can start fixing and improving the service, right? And then the change management. Change management is important because of the any change is a vector of an outage later, right? 70, 60, 80% of changes or of incidents that we have, right? They were triggered by a change that happened, right? So you need to have some safety in the sense of like validation tests and so on, but as well what we saw before about the global change vectors, right? You need to understand it really well of like, hey, this change that I'm doing, it has the property of being global, right? And might be fine, right? But you might need to say like, okay, this needs to be global because it's a central configuration file and so on, but how you are going to be able to test this, right, before it takes the service down. So all of this, there's something that operating the services is costly and it takes work, right? And the last section for the day is like, okay, how this translates into a role, right? My role is SRE, so I do this stuff, right? So what we do is basically, I'm a software engineer, right? But I'm running production, basically. So it's what happens when you have software engineers running something? We write software. That's what we do, right? So production is all infrastructure of code, is all CI/CD pipelines, all these things, all automated, basically, right? Because we just write code. I'm not going to run operations by hand, right? So I prefer to write a program that does it for me. But one of the properties that we have is that we are experts in distributed systems, right? In the sense of like, we know things that can fail, reliability, all these things, right? So when we look at system like Gmail, for example, software engineers, they are going to look at it from the perspective of like, what are the features that I need, right, for the users and so on, which is very important, right? But when I look at the same system from my perspective, I'm going to say like, ooh, how do I make this not failing all the time with this new feature is going to be deployed, right? So I might recommend to say like, hey, we need to replicate this JavaScript thing needs to be smaller, this whatever that is, right? And then it's like, proactive and reactive. So I'm on call, for example, when things break, I'm gonna be like responding. So that's reactive, I'm fixing it. But there is a lot of work that is proactive, right? There's like, okay, before things break, how can I prevent it to happen? Because the best outage or the shortest outage is the one that doesn't happen at all, right? And that's it, right? So the philosophy is that hope is not a strategy, right? So basically, failure happens. It's not that it might happen; it's that it's happening all the time, right? So you need to build a system that is resilient in something that is broken all the time. That's how we approach things, right? And then there is the automation and so on and so forth. So this is what we do. Just we have a book, by the way. So if you want to read, with all these details and so on, you can take it. I don't want you to like bother with the sales pitch now, but basically, if you are interested into systems and you're interested into software, you might be an SRE and you don't know it, right? So recap, like this is it. So basically, four takeaways that I want you to have, right? First, design systems from first principles, right? In the sense of like, this is the problem you have at hand. There are going to be trade-offs all the way, right? So you're going to need to choose, and there is not going to be a perfect choice. There's going to be things that they are great for performance, but reliability is not great, and vice versa. So it's your choice. You need to understand the problem that you are solving for, right? Faults. It's not that might happen, they're happening all the time. So you need to consider that, right? From the perspective. And then consider as well that the last takeaway is that more than 50% of the cost of software is not writing the software, it's maintaining it. So service management, monitoring, maintainability is very important to be considered, right? For basically for the existence of the service itself, right? So this is further information that you can have, right? So there is these books that you can read. There's information about how to design systems, response, and so on. Might not be everything, like the enterprise one might not be just relevant for you, but I think the first two they're gonna be useful for you to read if you are interested into the systems perspective of the software, right? That's all I have. So any questions? We had one question so far. Is there any other question?
Yeah, thank you very much. Let's see if more questions are coming in. So we had the one. If there are more online, just raise your hand. Are there questions here in the room? No questions yet?
That's okay. Sometimes it's hard to ask a question after an hour of a monologue. So like, take your time.
But if there are, like last year, also some students got in touch with you later, they find your email address or it's in the slides, I guess. So
yes, I'm gonna give you a copy of the slides in PDF, and I think it's going to be recorded, right? And then you can reach out in LinkedIn, email, whatever you want. There is a question in the chat. So Maxim asks, what does a person need to know to become an SRE at Google? That's a good question. I mean, I became an SRE at Google like 11 years ago, so probably the answer is going to be up to date, but I think it's going to be okay. So what I say, I'm a SWE, I'm a software engineer. So you need to know software, right? How to write it, what is the, all this stuff. There is going to be a perspective of systems, right? So software it's not something that runs in the vacuum, right? So you need to know like networks, for example, like some notions. So you don't need to be a network engineer, but you need to see like, live in the intersection of like, there is software, but there is as well systems, networks, like stuff like that, how that lays out in there, right? How change happens and so on. So basically do software, check out infrastructure, deploy your own software, right? And I think that's a very good starting point, right? There is a lot of things to learn in the way, but how to start is to do things in prod. Okay, we have Elme. Do you interview interns and student? What is expected from a student? We have internship running. So I think for this year, I think we are set because they run typically in summer, which is starting like the interns from this year they are running. But watch out for around September or something like that, like just after the summer, we start like doing the outreach for recruiting interns. And I think I was an intern, and it's a super great experience that I recommend you all to take. You come here from a few months, you learn, and it's fantastic. What is expected? What you do as a student, like, writing some software, like being able to like reason about things, being open-minded and learn, right? Because an internship is more a learning exercise for you than you to come in and deliver like few features to to the services. I mean, it's nice. You are going to write real stuff, and your stuff is going to end up in production, and you are going to see it in the services where you work on, right? But think about the internship as like an opportunity for you to learn how the real environment looks like, right? So that's the expectation, basically.
Yeah. Any questions now here in the room? So I really like your SRE philosophy, like don't blame, automate, and so forth. But I'd like to ask, what's the biggest fail that you had? How much % of the infrastructure did you crash?
Myself, I did one of the. This was a few years ago, so I think it can be spoken about. It was 100%. So one of the thing that we did is was in the authentication service we had one global vector that I was speaking about, right? This file that I was putting as an example is hanging somewhere on all the tasks and replicas read at once. That was not not random. So we had one file that you could use for saying like, hey, the last resort for blocking certain users, right? We just have it there for users that they are spammy, things like query of death, stuff like that. So you can put users in there for saying like, look, like we need to block the traffic from this user for the safety of the system, right? That file supported regular expressions, right? And you know that the plural of regular expression is problems, right? So I think I put a dot star or something in the way, and it matched any account, right? So 100% of it just dead. So we're recovering like a few seconds because like when everything goes on, all the alarms go out as well. But I think I'm still here. We learn from the mistake. We fix that, right? We did a post-mortem, right? So that's how we do it. We learn from the mistakes. And in this case, or in all cases, it's not me saying like, oh, Ramon wrote that thing, that's bad. It's not. Like the system allowed this failure to happen, and that's what needs to be fixed, right? The system should not allow this to happen. That was the postmortem side. Like we need to fix all this, so this mistake cannot happen again, right?
Yeah, perfect. Okay. Thank you very much for sharing that very personal story. There's another question asked: how much of your job have you automated already?
Good part of it, but think that this is like the coyote running like through the thing, in the sense of like the job is changing all the time. So new parts of the job are coming up. Like for example, I'm doing AI now. Like 10 years ago, I was not doing AI. So now we are working with like how to deploy LLMs, optimize them, like run agents, create agents for assisting us, and so on. That's a whole new part, right? So we optimized and automated like a lot of things for releases and stuff like that. That all this is new, right? It's like how you run with accelerators and these things. So all that needs new automation. So new we are optimizing all the job, but new parts of the job are coming up. So we are not running out of problems.
With there not being any further questions, I'd like to thank you, Ramon, for giving the guest lecture this year again, and we'll put it on YouTube. And if you have any questions or you're looking for a job, take a look at the Google website or get in touch with Ramon. And he posts a lot about AI infrastructure and this kind of stuff on LinkedIn, so definitely worth following. Thank you very much, Ramon.
Thank you all. This was very nice, and see you around. Ciao.
Take care. Bye-bye.
Ciao.